All right, next up is Euler's method. Yeah, it said Euler. Okay. What Euler's method is another method to approximate a solution for a differential equation, but this is like a value, the value of. Okay, and so what we're going to use is a bunch of um, tangent line approximations, or remember what we call local linearity, to solve, to estimate the value of on the curve. All right, so here's what we got. I got the actual solution. This would be the actual solution of the differential equation, or the particular solution. Okay, and what we're doing is we're going to start with a point on the particular solution. We're going to call it x sub 0. Okay, so this is the point x sub 0, oops, x sub 0, comma y sub 0. And we're going to, I want to evaluate at some other x value, let's say x sub 4. So what I need to do is split this up, the distance between x sub 0 and x sub 4, into 4 steps. So x sub 1, x sub 2, and x sub 3. From here, what we want to do is use our tangent line approximation to get from x sub 0, from y sub 0 to y sub 1. So the next y value. So I am going to draw in a tangent line here all the way to where x1 is, okay? And that is going to be where we estimate the y value of our, where we think x sub 1 is. So just to the right of our original point, okay? Then what we're going to do is we're going to make a second tangent line. So we're going to estimate the slope here, okay? And so it's a little steeper. And we're going to make another little tangent line that goes to x sub 2. Now we're going to get the slope at x sub 2, or we're going to approximate the slope at x sub 2, and draw in another tangent line that connects to x sub 3. You can see that we're a little bit off from the curve, but again, this is an approximation, okay? So we're going to estimate the slope of the tangent line at x sub 3, and it's getting steeper, so like so. And then at this point, we have our y value of x sub 4, comma y sub 4, and this is going to be the value that we approximate the curve to be at x sub 4, okay? So basically what we're doing at each one of these little steps is we are adding a little slope, okay? This is the change in y, or dy, and the change in x, dx. So in order to, so we're adding a slope at each point, between each point. I have a little system for you. So in order to figure out the step size is just dx, or delta x. You take the ending value minus the initial value and divide it by the number of steps, okay? We will start at some starting point, x sub 0, with its coordinating y value. And then from there, we find the slope at that x value. Then we find the change in y by multiplying the slope by the change in x. Okay, so our estimated change in y. And then we're going to find out our new y value, which would be our old y value plus the change in y, so the difference, and we get the next value to evaluate at, or the next point. Okay, so this is how we do this. We're going to approximate the y value of at 0.8, at x equals 0.8, using Euler's method, and 2 steps. Our differential equation is dy over dx is equal to x minus 2, and we're starting at y of 0 is equal to 5. So I noticed that right away, this is my a value, it's my x value that I'm starting at, and I want to finish at 0.8. So to find delta x, or dx, okay, we do b minus a over the number of steps. So I have 0.8 minus 0 over 2, which gives me 0.4. Now I'm going to set up my table. So I'm starting with x. I'm going to start with an x and a y value. And then we have a lot of other stuff. Okay, so I'm starting at 0, the 0.05, okay? And then I need to evaluate my table based off of my steps. So the change in x, or dx, we know is equal to 0.4. So I need to write 0.4 and then another step to 0.8. We will have our solution, or our estimation, when I get to this y value at 0.8. All right, the next thing we need to do is find the slope at x equals 0, or the 0, 5. So we do dy over dx. The slope is dy dx. And then we know that from the differential equation that the slope is x minus, can be calculated by the differential equation x minus 2. So I'm going to plug in 0 for x and 5 for y, but there is no y. So I'm going to do 0 minus 2 is equal to -2. Okay, that's our slope. Up next is to find the change in y. So in order to find the change in y, we're going to take the slope, the rate, okay? So dy is equal to the rate, m, times how long we're going to use that rate for. So we're doing -2 is the slope, and the change in x is 0.4. So I get the change in y would be -0.8. Then we're going to find the y new. So we're going to take the y old plus the change in y, or dy. Okay, so I take 5 because that's my y old. Okay, so 5 plus my change in y is -0.8, so that gives me a value, an estimated value of 4.2. Okay, that new 4.2 is the value is our estimated value at 0.4. Okay, now we do this again. Slope. So we're going to plug in the 0.4 and 4.2 into the differential equation. So I get 0.4 minus 2, which gives me -1.6. Then the change in y is equal to the slope, so -1.6 times 0.4, our step, which gives us -0.64. All right, up next is the new y. So I'm going to take my old y, 4.2, and add on the change in y. So it's -0.64, okay, which gives me 3.56. Okay, so that is going to be our estimated value at 0.8. I made my cloud too small. Okay, so we know, I always put the little cloud there so I remember to stop and you don't keep filling in this table, okay? What I know is that y of 0.8 is about equal to, it's super important that you put the about equal to, because this is an estimation. It's about equal to the y value of 3.56. Okay, so again, this is using Euler's method to approximate the value of a differential equation, the solution to a differential equation. Okay, the next part is we're going to actually solve this out because we want to be able to compare our work to see how close we are. Okay, so again, these methods usually are used when we can't solve a differential equation, but you know, we're just going to make all the connections here. dy dx is equal to x minus 2. Okay, separate and integrate. I get dy is equal to x minus 2 dx. Integrate. So I end up with y is equal to 1/2 x squared minus 2x plus c plus c. I'm just going to leave it because we already solved for y. Okay. Then we're going to get so this is our general solution. Let's get our particular solution. Okay. I'm plugging in the point 0, 5 because that's our initial condition. Okay. So I end up with 5 is equal to 1/2 times 0 squared minus 2 times 0 plus c. So I can see that c is equal to 5. So my particular solution that passes through the point 0.05 is 1/2 x squared minus 2x plus 5. All right, that's my particular solution. And then we're going to use that particular solution to evaluate at x is equal to 0.8. So we're going to plug in y of 0.8, and that would be 1/2 times 0.8 squared minus 2 times 0.8 plus 5. And I end up with, I used a calculator outside, equals to 3.72. So the exact value of 3.72. So this is the exact value. Okay, and from Euler's, we had our estimation of 3, it's on that other paper, about equal to 3.56. Okay, I noticed that our estimation was an underestimate. So what does that tell you about the concavity of the curve? So because our estimation was an underestimate, the graph is concave up at 0.8. So the tangent lines are below the graph. Okay, cool. Next up, we're going to do another one of these. So if dy over dx is equal to 2x minus y, and y is equal to 3 when x is equal to 2, and use Euler's method with 3 steps to approximate y when x is equal to 1.7. So I see I have my differential equation. Okay, I see I have an ordered pair. And I am going to be using 3 steps, and I'm going to have an ending value of 1.7. Okay, and my starting value is x is equal to 2. So that's my a value. Okay, so we're going to find dx first, figure out our steps, and set up our table. Okay, so I do b minus a, so 1.7 minus 2 over 3 steps gives me negative 0.1. Yeah, negative 0.1. So when I set up my table, I have my x, my y, and then a bunch of space. Okay. So we're going to start with x is equal to 2 and a coordinating y value of 3. We're going to put in my change in x. So subtract 0.1. So I get 1.9. I'm going to leave more space. 1.9, 1.8, and then 1.7. And remember, you got to make your cloud so that you don't forget to stop calculating. Okay, so next up, we get our slope. So I usually just write it into x minus y so that I don't forget what I'm doing. Okay, so we're going to plug in the point 2 and 3. So 2 times 2 minus 3 gives me a value of 1. Then we're going to figure out our change. That helps me figure out my change in y, which is the slope times dx. The slope is 1. and we're using that slope for a distance of negative 0.1 in the x direction, which gives me a change in y of negative 0.1. All right, finding our new y value is equal to y old plus the change in y, or if you write delta y, that's fine too. Okay, so we get 3 is our old y minus 0.1, so 2.9. So at 1.9, we're estimating the y value to be 2.9. All right, repeat the process. So we're going to do 2 times 1.9, because that's our x value, minus our y of 2.9, gives me a value of 0.9. Get the slope. Oh, we got the slope. It's 0.9 times negative 0.1 equals negative 0.09. That's our change in y. The new y is 2.9 plus our change in y, so 0.09, which gives us a value of, now we're at 2.81. Okay, one more time, because we just got to make it to the cloud. Okay, so 2 times 1.8 minus our y value, so 2.81, is equal to 0.79. The slope times the change in x gives me the change in y. So 0.79 times negative 0.1 is negative 0.079. Old y is 2.81 minus our new, or plus our new, which is negative 0.079, which gives me a value of 2.731. I could do better than that. 2.731. So in the cloud, that I again made too small, is 2.731. So y of 1.7 can be estimated to a value of 2.731. All right, so the solution at 1.7, at x equals 1.7, is going to be 2.731, or is about 2.731. Okay, we're going to do another one, but this time I'm giving you a table. So the table shows us our x values, our f prime of x, and our f of x. And what we want to do is use Euler's method to using 2 equal steps, so that's n, to approximate the value of 2.6, f of 2.6. So that is my ending value b. So where are we starting from? It looks like we're starting from a value of 3, and then we're going to 2.8, and then 2.6. So I can see these 2 steps happening here. They're evenly spaced out for me. I'm ending at the place I want to end up at as 2.6, and I'm starting at 3. So it looks like we have a delta x is equal to 2.6 over minus 3 over 2, which gives us a value of negative 0.2 for our change in x. I'm going to set up my table because I hate the way this one is organized. So I'm going to start with my x, lots of space, my y, lots of space, okay? Starting with 3 and a coordinating y value of 2. Okay, got to make my 2 jumps. So I'm going to go from 3 to 2.8 and then 2.8 to 2.6, and I end up with my solution right here. Okay, so I now need to find the slope, which remember is dy dx. So what is the slope at x equals 3? Well, isn't that f prime of x? Yes. So the slope is 0.4. So now can I calculate dy? Yes, that's the slope times dx, remember? So the slope is 0.4. My change in x is negative 0.2. giving me a change in y of negative 0.08. Okay, and then my y new, I just was going to write u. Okay, my y new is going to be 2 minus 0.08, which is equal to 1.92. Okay, so I'm going to write my 1.92 right here. Okay, and I am looking at what is the slope when x is equal to 2.8. Oh yeah, in the table, it was already there. X is equal to 2.8, and the slope is 0.7. 0.7. Okay, I forgot a 2 on my paper. I'll fix it. Anyway, not on the notes, so. Okay, so now I'm going to find my dy. It's 0.7 times negative 0.2 is equal to negative 0.14. My y new is y old, 1.92 minus 0.14, which gives me 1.78. So y of, actually, this is written in f, so f of 2.6 is about equal to 1.78. All right, last example. Okay. So we're going to consider, this is going to have a lot of fun stuff to do. So the differential equation is dy over dx is equal to y squared times 2x plus 2. And we're going to let y equal f of x be the particular solution to the differential equation with the initial condition of f of 0 is equal to negative 1. First off, let's find this limit. So the limit as x approaches 0 of f of x plus 1 is equal to sine of x. All right, so for funsies, why don't we just direct substitute and see what happens? Yeah. All right, so I'm going to direct substitute, and I get f of 0 plus 1 over the sine of 0. Oh yeah, I remember. F of 0 is equal to negative 1. Right? So I get negative 1 plus 1 over 0. Oh, I see. 0 over 0, that is, we're going to apply L'Hopital. Because of the indeterminate form. Okay, so let's take the derivative of the numerator. The limit as x approaches 0. And so the derivative of f of x is f prime of x. The derivative of 1 is 0 over the derivative of sine of x, which is cosine of x. Okay, and then I now know that what I'm going to do, this looks crazy, but I have an equation for f prime of x. F prime of x is dy dx. That's this. Y squared times 2x plus 2 all over the cosine of x. All right, now let's direct substitute. Okay, and so I'm going to tackle all the x parts first. So 2 times 0 plus 2 all over the cosine of 0. And then I'm like, what is this y out here? Okay, remember that y is equal to f of x, right? So really what I'm plugging into is f of 0, all of that squared. What is f of 0? Oh, yes. Remember, f of 0 is equal to negative 1. So I can substitute this my y squared, or f of 0 squared, as negative 1 squared times 2 times, I'm just going to rewrite it, 2 times 0 plus 2 all over the cosine of 0. So now what I get is negative 1 squared is 1 times 2 over the cosine of 0, which is 1. So this limit is equal to 2. that was fun. Okay, that's like circle thinking. Okay, we're going to use Euler's method. 2 equals, starting at x is equal to 0, 2 equal steps. We're going to approximate the value of 0, x is equal to 0.5. So I'm starting at 0. I want 2 equal steps. I got to make it to 0.5. So my dx is equal to, I know you can do this in your head, 0.5 minus 0 over 2, which gives me a value of 0.25. So I need to change by 0.25, okay? And the coordinating y value when x is equal to 0 is, oh yeah, when x is equal to 0, y is equal to -1. Okay, we need to get our slope, which is dy dx. Okay, and I need to write it down. So I get y squared times 2x plus 2. Okay, dy is equal to the slope times dx. And then we need to get our y new. Okay, so we can start plugging this in. I'm going to plug in 0 and -1. So I get -1 squared times 2 times 0 is 0 plus 2, which gives me 2. dy would be the slope, so the rate of change times the distance of that change, which would be 2 times 0.25, which is 0.5. Okay. Then I'm going to plug into y new. So I have -1 plus 0.5, which is -0.5. Okay, substitute that in to our table, and I am going to write my cloud turned into a rectangle, but there it is. Okay, so -0.5 is my y squared times 2 times x, which is 0.25, plus 2, which gives me a value of 0.625. Okay, so the slope is 0.625 times 0.25, and that equals 0.15625, and I am over these decimals, so I used my math enter in my calculator, and I got 5 over 32 as my fraction. Okay, so my y old is -1/2 plus 5 over 32. Again, I used a calculator and did math enter, though you could do this by hand. I know you can. I get -11 over 32. So when x is equal to 0.5, we're estimating the value of our solution to be -11 over 32. So f of 0.5 is equal to -11 over 32. Okay. Okay, so for extra fun times, we're going to go ahead and find the particular solution to our differential equation given our initial condition, and then we're going to plug in to figure out what the value. Oh, well, let's just start there. Okay, so I get dy over dx, and this is our last example, is equal to y squared times x, 2x plus 2. Separate and integrate. So I get dy over y squared is equal to 2x plus 2 dx. All right, I'm going to rewrite this. Y to the -2 dy is equal to 2x plus 2 dx. Now we integrate. So I get negative y to the -1 is equal to x squared, 2x squared over 2. So that would be x squared plus 2x plus c1. All right, divide by negative. Actually, I'm going to rewrite this. -1 over y, yeah, is equal to x squared plus 2x plus c1. My brain is going a little funny. Okay, multiply both sides by y. So I get -1 is equal to x squared plus 2x plus c1 times y, and then divide both sides by this. So I get y is equal to -1 over x squared plus 2x plus c1. Notice the c1 is in the denominator. I'm going to leave it there. It's part of that polynomial in the bottom. Okay. All right. So up next is to find my c value. Find c. With the point f of 0 is equal to -1. So I have -1 is equal, yeah, y is -1. So -1 is equal to -1 over all the x's are going to go to 0. So 0 squared plus 2 times 0 plus c1. Okay. So now I'm going to simplify. I'm just going to rewrite it. -1 is equal to -1 over c1. I am just going to flip these. So I have -1 is equal to negative c1. So c1 is equal to 1. So y, my particular solution, is equal to -1 over x squared plus 2x plus 1. Okay. For fun, I know I said that was it, but let's just evaluate y of 1/2 and compare it to part B. Okay, when I plugged in 1/2 in for x's here, what I got was negative 0.547. And from part B, we got, using Euler, y of 1/2 is about equal to negative 0.3437. Hey, that's not so bad. It's only like 0.2 off from the actual solution at x is equal to 1. Now, again, our estimate is that an overestimate or an underestimate? So it's an overestimate because negative 0.3 is larger than negative 0.5. So the curve is concave down at 1/2. Okay, and that is it.